Okay, so today's lecture has a bit weird name, the Pigeonhole Principle. And you might ask, is this a name or what does this mean? No, pigeon is a pigeon and hole is a hole. And it's about the following image, if you want. We have, let's say for simplicity, we have a coop, a pigeon coop, that's where they keep pigeons, and it has 4 holes, okay, boxes, whatever you call them, 4 nests, whatever you like to call that. And you have 5 pigeons. You see that there's a bit of a problem now, right? Because if you want to put one pigeon, I'm not going to draw pigeons, my pigeon's going to look like this, okay? You can put one there, you can put one there, and one there. So you have 5 pigeons, right? Here they are. And so I have already put 4, but the 5th one has to be sharing a room, so to speak, right? So there is this has to be at least one that has 2. Now there are different solutions. For instance, I could also do it this way instead this way, and I still have 1 free. Okay, I could put 2 there, 2 there, 2 there. Okay. But what I never can do, whatever I try to do, I always end up with at least one of the holes having 2 pigeons. Now, why is that? Well, there are 4 holes and there are 5 pigeons. There are just too many pigeons for holes, right? So 4 is smaller than 5, let me write it that, and it means at least one hole with 2 pigeons. It doesn't mean that there is a hole with exactly 2 pigeons. Again, here's a solution. Suppose these 3 like to be together and these 2 are separate. Then these are 5 pigeons over 4 holes, but there is no hole with 2 pigeons. That's why I have to say at least 2 pigeons. Okay. Also, it doesn't mean that there's exactly one hole with 2 pigeons. This is exactly here. This example here we see there are 2 holes with 2 pigeons. Okay. And of course, there is also a solution, like let's say, imagine that one of the pigeons is female and the other 4 are like suitors, then you might end up with something like this, right? So, okay, all possibilities are there, but every single of these has the property that at least one of the holes has 2 pigeons. There might be more holes with 2 pigeons, there might be holes with more than 2 pigeons, there might actually be no hole with 2 pigeons, but with more than 2 pigeons, but at least one hole with 2 pigeons. That's what they call the pigeonhole principle. And of course, what's the more generally, that is if you have n pigeons and less than n holes. I'm not making you say how many, but if it's less, then it's still, we have again the same conclusion here. That's what the pigeonhole principle tells us. There are nicer pictures if you want in. And there are a lot of, this is an important principle. It's very simple, right? Everybody agrees with it. If you look at it, think a bit about it, it's quite simple, but there are quite nice things you can do with it. Okay, so let's see. So let's see here. So suppose you have 400 students in a big auditorium. Yeah. Then I'm claiming at least 2 have the same birthday. Okay, let's think about this. So then at least 2 have the same birthday. So here is an application of the Pigeonhole principle. So how do we analyze this? Well, this, of course, there are no pigeons here and there are no holes here. So what we're going to do is we are talking about the pigeons between quotes, yeah, and then the holes between quotes. And then we just have to say, what are they? In this case, what are the pigeons? Well, that are the students, right? And what are the holes? I mean, that might be still, but what are the holes here? That sometimes there's nothing material here. There's not a physical object here. The holes are here. The days of the year, because that's everybody fits exactly in one day of the year. The holes are the days of the year. Okay. So the first thing you have to do is decide what are your pigeons and what your holes. So let's call this step 1. Okay. Then step 2 is now you can put numbers. That's sometimes you know, sometimes you don't know. We'll see many applications of this. So we know how many students there are. There are 400 students. We also know how many days of the year there are. Well, it depends a bit on the leap year, or so there are 365 or perhaps 366. But it doesn't matter here because look what we have. So this is our n here. And so we have 400 pigeons that only fit in less a number, 365, 366, doesn't matter, less number of holes. So this proves that at least 2 pigeons are in the same hole. What does it mean? At least 2 students are born on the same day of the year. Okay, so this is how we apply this. Now it's sometimes not so. Some applications are quite nice. They are a little bit more clever. So I'm giving you once in a while a clever one, but for the homeworks and for the tests and so I'm going to ask you more straightforward ones. Okay, but here's the clever one. So given a number, let's call the number k. K is a number 1, 2, 3, 4, 5, 6, 7, something like that. So k is a number, a natural number. Let's say at least 1, or at least perhaps, I think, let's call it at least 2. Okay, and so I'm claiming that yeah, there is a multiple of k, of this number k, whose digits are all zeros or ones. Okay. Now, of course, I can take k equal 2, and then it's kind of obvious, right? 10 is a number that's a multiple of 2. Okay. Can you do it for 3? Yeah, for instance, 111 is divisible by 3. That's an example. Okay. So what about k is 5? Let's try to think a little bit. But again, it's very simple, right? The number 1... yeah, so the number 10, for instance, has digits only 1 and 0. That is clearly divisible by 10. So this is a solution, right? So for every number, I have to give you a multiple of that number so that its digits are just 1s and 0s. Let's do for k equals 6. That might be the first thing that you have to think a little bit about it. And you might try here. I'm not so sure what I see immediately what I should do here. But I think this one is okay. I think this is divisible by 6. Because it's an even number and it's also divisible by 3, so it's divisible by 6. But that's already a little bit, okay, you need to know a little bit number. But this is also true if I take k equal to 5,320,517. Don't ask me again what my number was. I don't remember it anymore. But any number k. Okay, so here's the proof that is the case. Okay. So what are going to be my my pigeons here? My pigeons are going to be the following numbers: 1, 11, 111, 1111 in digits, right? These are decimals, okay? Don't think that I'm talking about binary here. I'm talking about decimals, right? Decimal numbers, the usual numbers. But I'll keep writing them, and I'm gonna do 1, 1, 1, 1, 1. Just so, in other words, all the numbers that only have ones in them. And how many is this one here? I have k plus 1. Okay. So how many numbers are there? Well, we'll talk about that. So these are my pigeons. So the number of pigeons. So n. That's the number of pigeons, right? The number of pigeons. I'm going to always use capital N for the number of pigeons. The number of pigeons here is, well, there's 1, 2, 3, k plus 1. Are you agree with that? Okay. Okay, now, the residue residues or remainders mod k. These are going to be, sorry, I should have said this, these are going to be my holes. Okay, every number has a remainder when you divide it by a given k here. Okay, so for instance, if I have k is 6, what are my possible remainders? 0, 1, 2, 3, 4, and 5. So how many possible remainders are there? So there are k possible remainders, right? Exactly as many as the number you divide by. You agree with that? If I divide by 6, the possible remainders are 0, 1, 2, 3, 4, and 5. That's by definition, okay? So there are exactly 6 of them. So in general, if I divide by k, there are possible k remainders. So let's see, we're in a situation where we have more pigeons than holes. Okay, so this means that among this list that I have here, okay, among this number list that I have, 2 have the same remainder when I divide by k. Okay, so I don't know what they are, so let's call this a1, this is a2, a3, and then this is an ak plus 1. Okay, so there's an ai that is equal aj mod k. They have the same remainder modulo k. That's how we note this. If you go back, see what we did this in discrete one. So there's an I that is less than j. AI is the first one that I have like that, and aj is the second one. As I said, there are at least 2. Okay, there could be many, many more, but I don't care about that. I just take the first and the second one that I see. AI and aj. Okay. Now let's think about, let's for simplicity say this was this number and aj is the bigger one, so it has more numbers. Okay, now subtract one from the other. Well, of course I should subtract it this way then, I guess. There were 6 of those. So this what I would have called this a6, right? This 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This would be a10. Okay, so let's take the subtraction here. What does that number look like? Well, 4 ones and then 6 zeros, right? Now, what does it mean that you have the same remainder mod k? That means that k divides the difference, aj minus ai. This is exactly what I did here. So I know that if this would have been the 2 choices, and I just to just visually see that if I subtract one from the other, the result is something that starts with ones and then ends with zeros. Okay, and it is divisible by k. In other words, this number here, this number is a multiple of k. And this number, whatever this number is, aj minus ai, consists of ones followed by zeros. So it's even a bit more specific than what I claimed in the beginning. Okay, there's a multiple of k where digits are all zeros and ones. And actually, more precisely, there's a multiple of k such that the first that starts with ones and then a bunch of zeros, a bunch of ones followed by a bunch of zeros. Okay, so that's an application. Now, what we gonna do, and that's even more interesting, is the generalized pigeonhole principle. Generalized pigeonhole principle. Okay, so what is this? Okay. So let's look at our original example, but let's make it slightly. So I'm doing all possible. I'm still getting here and there things got lost. But let's say I still have 4 holes. Okay, 4 holes. But the number of pigeons. Let's change the number of pigeons here. Okay, let's change the number of pigeons. I have 9 pigeons. Okay. Okay, so here are my pigeons, 4, 5, 6, 7, 8, 9. I'm going to put them in there randomly, this one, and then say the next one in the same. And then I'm going to put one here, and then one here. I hope you understand this is random that I'm doing, and then I put there one, and then I put one there, and then I put one there again, and then I say, okay, I put this one there. Now look at the result. This is random-ish, right? I see that I have at least one hole with not just two, which we know because there are more pigeons than holes, so at least one will have two pigeons in it, but there are even holes with three. Okay, so let's think, is this always true? Okay, so what you can now try to convince yourself is that it's not possible. I cannot, sorry, that is always, I can never make an put my pigeons in my holes, in my coop, if there are at least not three in one of the holes. Because look, if I try to do it as best as I can, I'm saying, okay, you two, you go in the first, okay, because, and now it's filled. I don't want to put more than two in a hole. Then these two I have to put there, and then next two have to go there, I have no choice, and then these two have to go there, and then you, okay, I'm gonna have a pigeon for lunch, for dinner. No, I have to put it somewhere, and I'm forced to make at least one having three in there. Okay, so how does that work? Okay, so let's analyze this now. What's the formula here? So we have n pigeons. I said this is going to always be my n. I haven't used this letter yet, little k, not the big K from the example, but I'm always going to use little k for the number of holes. And m is the least number that has to occur at once. Okay, I have to have at least once that has that many in there. Okay, so in this case, in our previous case, n was at 9 pigeons. I had 4 holes, and the conclusion was there were at least 3 that were in one hole. At least the least number that has to occur in one hole. That has to occur, or let's say, let's phrase it with our holes. The least, the least number occupying one of the holes. No, and that's not the right way of saying that. I should say it differently. It's at least one hole has to have that many. Sorry, I should say it that way. At least one hole with at least this many M pigeons in there. And what's the formula now? Okay, so the formula is this. N divided by k, if you have n pigeons dividing over k many holes. Now, of course, in general, this is a fraction. It's not going to have it's not just a nice quotient. I have to take the floor of this number, and the claim is that this is always bigger than m. So in our case, let's verify this formula here. In our case, okay, is this the case? 9 divided by 4, I have to take the floor of that. Now, 9 divided by 4 is 2.25. So it's the floor of 2.25, which is 3, right? Remember, I'm so sorry. I keep saying floor, and I mean ceiling. So the ceiling. I was standing on my head when I was saying this. That's why I got confused. Okay, so the ceiling of 2.25, that will be the next integer, right? That's 3 here, and that's why we have at least 3 pigeons in one of the holes. Okay, so that's how this works. So let's look at some examples that we have of this. We can look at simple examples first, and then we're gonna ratchet up a little bit. Okay, so 100 people in a room. Let's say, how many are born at least in the same month? At least how many in the same month? Same month. Okay, So let's analyze this. We have to, step one, as I said, we're going to have to decide what are our pigeons and what are our holes. Okay, so what are the pigeons here? Let's think about this. I mean, again, as always, when I'm doing examples and explained everything, at this point you might be able to solve this question. You actually should be able to if you listened well, or you could try at least and see whether you understood what I was saying. So pause the video, try to figure it out yourself, and then move on. Okay, what are the pigeons? Well, the pigeons are the people in the room, right? And what are now the holes here? That are the 12 months, the months of the year. Because I'm gonna think of every person. I'm gonna basically ask, what month are you born? Okay, think of that way. So that's step one. Step two is, well, what are the numbers? Remember, N and K. Well, how many people are there? There are 100 people, that is given. And how many months are there? Well, we all know there are 12 months in the year. Okay. So the result is now M is, so we have to calculate the following number. Let me put it this way. Where is my formula here? Here's my formula. So M, sorry, I don't know why I wrote, I'm sorry, I was thinking about this. Why did I wrote here? This is what I mean, the least number, okay? So M is the ceiling of N divided by K, okay? So N is 100 here, oh, not ceiling, not 100 divided by 12. 100 divided by 12 is, well, let me tell you how much it is exactly. 100 divided by 12 is 8.33. And so the ceiling of that is 9. So of 100 people, at least 9 of them are born in the same month. Now that doesn't mean, I'm not saying that at least 9 of them are born in February. That makes it, that's a different thing. We'll see, well, I'll give you an example a little bit later about that. Well, let's do the next example, but it says that at least 9 people, see here, let's do the next one. We have a deck of cards. Now, deck of cards are things that happen a lot in this kind of problems. And some of you are not don't like cards games perhaps that much, but it is important. So a deck of cards has 52 cards in it, and there are 4 suits: hearts, clubs, spades, and diamonds. Okay, so how many cards do I have a draw to have at least 3 of the same color, of the same suit? So how many cards to draw to have at least 3 of the same suit? Okay, so let's analyze this. Now you see, it's not okay. What are the pigeons here? Well, the pigeons are the cards that I'm drawing. What are the holes? Well, the suits, right? Okay. So I put this. Okay. So what are the cards? The drawn cards. I should put this drawn cards. I'm drawing cards. So what is N here? Now you say 52. No, N is the number of cards I draw. Of course, it can never be more than 52 because there are only 52 cards. But N is I don't know yet. That's the question. How many cards? So I don't know N. So N I don't know. How many suits are there? Well, I just said K is 4. Now, I have to have at least 3 of the same suit. So here M is 3. So I have to solve this here. Now, when is 3 equal to N over 4? What is the least N that I can take here? Okay. So how do you solve an equation like that? Okay. So let's write down a general formula for this. I have to be careful that I don't go out of juice here. So let's first figure this out here. What would this be? okay? So let's think about this. When would this fail here if I would have 8, right? If I have 8 cards, so if n is 8, then I have 8 divided by 4 is 2, and the floor of that, the ceiling of that, sorry, is 2, not 3. So 8 is too little, it's too few. But if I add 1 to it, n equals 9, then 9 divided by 4 is the 2 point something, and therefore its ceiling is 3, and so I'm done. Okay? So how to find this? So this is now actually basically solving this formula here, but this time we have to solve the formula where we don't know n or n, unless, as we'll see later, we might also know k. So how do you do this? So I want to discuss this very quickly. So when you're trying to solve this thing here, equal or perhaps even bigger than m. So remember, n is the number of pigeons, k is the number of holes, and m is the least number of pigeons per hole. In at least one hole has this many pigeons. Okay, that's what we're trying to do. So in order for this to be hold, what we need is that m has to be at least k times m minus 1 plus 1. Okay. Of course, we want the least one, so we actually take n to be, so we try to find the least n, we would solve it this way, okay? Or, this tells me what n would be. So if I have k and m, then this is what m would be. Let's think about it, why is this the case? Well, if n is of this form, if n would be k times m minus 1, okay, then n divided by k, that is m minus 1, and the floor of this, the ceiling of this thing is just n minus 1. Because n minus 1 is a number, right? It's a whole number. This is too little. So, and it's too little, even if I add 1 to it, that's exactly the plus 1 here, then I am okay. So this is how we solve this inequality, we solve this problem here if we need to find n. So, for instance, let's think about this. We have n students. No, let me write it. I'm a bit worried that I'm getting out of juice. I want to go. So we have students of age 18 to 21. So 4 different, 18, 19, 20, and 21. Okay. So how many students need to be in class? So n is the students in the class. Be in a class to have at least 4 of the same age. Okay, so let's solve this. Okay. So again, what are the pigeons here? Well, the pigeons are the students. Sorry, pigeons are noble animals. Okay, well, they're smart because they know how to get back home. Pigeons are the students. What are the holes here? What do you think the holes are? The age groups. Okay, so the age. Okay, and then. Okay, so that's step 1. So what is n? Well, n is the thing that we don't know, because we ask how many students do you want. What are the age groups? How many age groups are there? Well, 18, 19, 20, and 21. Okay, let's say only these ages that we allow. So 4 age groups. So what we need? What is m here? So m is at least how many we want. We want to have at least 4 of the same age. So m is 4. So we're solving this n divided by k is equal to n divided by 4 is equal to 4. Now by the formula, what is this? Okay, so we subtract one of this number. So we do this, we do this one, we do 4 minus 1. We multiply it with this number, that's the k, 4, and then we add 1 to it. Okay, this is what this formula tells me. Okay, so what is this? 3 times 4, 12 plus 1 is 13. So at least 13 students I need. Okay, so let's do one more, and then the rest I'll leave for homework problems, and we go over reviews and so on. So the one I want to do is this here. Okay, yes. Let's say I have 50 t-shirts. No, I have 50 flyers. Sorry, 50 flyers. And I want to print them in various colors to just see how they come out. But I want to have at least one sample that there's already by family members. I want to give them my flyer, okay? And so there are. So how many flyers? Sorry, how many colors? So let's say color. Each flyer is in one color. I mean the paper is in one color. How many colors can I use? Should I use? Can I use? Should I use? So flyers on different papers, right? So you used to have at least 6 of the same color. As I said, I want to give this already out to six people I know, and I don't want them to think, oh, why did I get a pink and he got a blue one? Okay, I want them all to be same color. Don't mind what color it is, at least that. Okay, so let's analyze this again. What are our pigeons with our holes? And what is here, if you want, M? Let's just call it M. The least number here. Okay, so what are the pigeons here? The flyers, right? Okay, it's the flyers. What are the holes? Well, the colors that I'm going to use to color it. And M, okay, that is the least that I want. So what is N? Do I know N? Yes, I know. There are 50. So I know N. Okay. What else do I know? Do I know the number of colors? No, that's the question. How many colors are there? So this one I don't know. And M, well, I need at least 6 of the same color. So M is 6. Okay. So now we have again the same thing. 50 divided by K is equal to 6. Okay. So what K should I use? And the formula is the same. 50 is, remember, subtract one of this number, 5, multiply with K and add 1 to it. Okay. This is the formula that I had here, right? Okay. So what is this now? This is 49 is equal to 5k. So that means that k is equal to 49 over 5. Now, of course, that's not a whole number here. And so what is this? I have to take the ceiling. Sorry, now I say sitting on the right floor, right? I have to take the floor of this number, and that is 9. Let's think about it, right? Why do I need to do that? Well, if I would take, you would say, you might feel, yeah, I want to take the ceiling here, 10. But no, look at what happens if you take 10 in this formula. If you take 10 in this formula, then 50 divided by 10 is 5, which is not 6, right? So because, of course, why is it that we take here the lower value? Because it's in the denominator. That's why we make the smaller there, right? And when it's in the numerator, that's why we take the ceiling. Okay, I hope that the difference between why we take ceiling there and floor here. Okay, so that's the solution here, 9. Okay, so that's a couple of I think we have now I discussed everything, and then I leave everything to the homeworks, otherwise I'm running out of juice here, and also I don't want to make these videos too long. Okay.